Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures on interference in optics, and now we pass on to the phenomenon of diffraction of light. And in this lecture number 19, the contents will be diffraction effects, Huygens principle, Huygens construction of spherical wavefront, rectilinear propagation of light. Now, let us begin with diffraction of sound. In the earlier lecture, I told diffraction means bending of light beam. As far as light waves are concerned, they undergo diffraction. By this, what we mean is the light waves will undergo a bending, right, will experience some bending of light, right. On the other hand, supposing you are sticking to Newton's theory of light, if you assume light to be travelling in the form of rays, light ray will be going here, then there will be nothing seen here, right, the bending will not be there, bending cannot be there. On the other hand, if light is considered to be made of waves, then only bending can be present, will be there. And in order to explain that, or in order to understand that, we are talking about sound waves. You know, when you are talking about sound waves, I am in a room, I am sitting here, and when I am talking, the neighbor can overhear because the sound waves bend. That is what I am showing here. The people are making a lot of noise here. The school band is on, the people are playing the musical instruments, the band is on, the teacher is far away, he is coming in the veranda, still he is able to hear the noise or hear the sound made by these people who are playing drums. It is possible because the light waves are having long wavelengths, they undergo bending and it reaches the ears of the teacher. Light waves have longer wavelengths, they can bend. Sound waves having a longer wavelength, and similarly light waves also have longer wavelength and they can bend, right, they can bend. So, the wavelength of the wave, light wave, and the obstacle size, these things matter, I will come to that later, but the point is light waves can bend and this bending is known as diffraction of light. Okay. Now, you ask the question radio wave diffraction, whether radio waves undergo diffraction, whether TV signals can undergo diffraction. What is the problem with the TV signal and radio signal? How can houses in the shadows of hills, you have got a hill here, the hill may be even having greater height, the house is somewhat at lower level, right, the signal is coming here, radio signal is coming here. If it would have gone straight like what Newton said about light ray, light to be made of rays, they will travel in a straight line, the light ray, the signal that is coming here, it goes straight. It will never reach the persons who are sitting inside the house, there is a house here, right. Now, the radio waves undergo diffraction, right, and the bending is there, and that is the reason why the radio waves reach the houses. The radio signals are of longer wavelengths, they can be be bent around obstacles. You got a mountain or a hill, they will undergo diffraction and they will reach the radio waves diffract around a hill to the house, right. There is a house here. All electromagnetic radiation travels in straight lines. Electromagnetic radiation is traveling, but still the wave nature is there and the bending is there and it reaches the house. On the other hand, wavelength of the waves is shorter, as it happens in the case of TV signals. The wavelength of the waves is shorter, the spreading or the diffraction effect will be much smaller. That is the reason why if the TV signal becomes weak, supposing you have got a TV station here, the TV station, the signal that is received will be much weaker. On the other hand, radio waves will undergo the longer wavelengths, the radio waves will undergo diffraction, they will reach the person here. On the other hand, the TV signal will not reach or it becomes weak. So, this explains why television waves are much more difficult to receive in hilly areas than radio waves which have longer wavelength. The radio waves have longer wavelength, that is the reason why they undergo diffraction and why the diffraction effect of light is so difficult to observe. Passage of waves through an opening. As I told you in the last lecture, if there is an opening, then if the opening the size is very small, then the diffraction effect will be profound. As I will be showing in the next slide, if the size of the opening is small, diffraction effect will be larger. When opening is large compared to the wavelength, light waves do not bend around the edges. What is diffraction? It is bending. Here there will be no bending. When there is no bending, the wavelength is large. When the opening is large compared to the wavelength, the opening is large, the bending will not be there. When the opening is small, the bending is noticeable. Diffraction effect becomes noticeable. When the opening is very small, the waves spread over the entire surface behind the opening. You see here, when the opening is wide gap means small diffraction. Okay, the bending is much weaker, but here the bending is much more pronounced. When you see notice the gap, it is very small. Here it is very large. If the gap is very large, the bending will be smaller. Bending means what? Diffraction effects will be less pronounced. Here more pronounced, because the gap decides the diffraction. Narrow gap leads to large diffraction. So, if diffraction effect were to be observed, the gap through which the light wave is passing through should be small. That is the important point. Light wave that is passing through the obstacle or a pinhole should be small. Then only the diffraction effect will be pronounced, can be observed. Some other diffraction effects, which of course they go unnoticed and we are not interested or given here. As I told you in the last lecture, the CD which is shown to sunlight or white light, when you tilt it, you see the different colors, and the colors which are appearing or observed are due to the phenomenon of diffraction. Similarly, keep a blade and look at the edges of the blade. You show the blade against the white light, you see at the edges, you can see even a cloth kept near the window, you can see lines. And similarly, around the blade, if it is kept near a source, you should have the proper eye to see, to observe the diffraction effects. Around the blade there will be lines formed, and similarly the colors that are exhibited or possessed by fine birds, the colors are due to again the phenomenon of diffraction. Now, we will pass on to Huygens Fresnel theory. Now, how to explain the propagation of light waves? Huygens proposed the light that is going from a source, yes, you have what are called wave fronts. Light is going, you have a wave front, then again the wave front travels like this. And what is meant by spherical wave front? What is meant by a progressive, how the light is getting transmitted from the source to some other point. Each progressive wave produces secondary waves, the envelope of which forms the secondary wave front. As I will show you here, S is a monochromatic source of light, this is the primary wave front, PQR is called the primary wave front, according to Huygens and Fresnel, in those years when the wave theory was proposed, they talked about all pervading ether. All throughout the universe, you have a medium called ether. A medium is required for the propagation of light wave. For the propagation of wave in water, you got water the medium. Similarly, how does a person hear? You got air. Whether you will be able to hear what I am talking, if you are in a room completely evacuated, there is no air at all. If there is no air, you cannot hear. Sound waves require a medium. You have got air as a medium. So, every wave requires a medium. So, it made Fresnel to talk about ether, all pervading ether. So, ether is present everywhere, and PQR refers to what is called a primary wavefront. You got secondary wavefront is a P prime, Q prime, R prime is called a secondary wavefront. Point source here, the wavefront originating from the point source of light at a finite distance is called a spherical wavefront. Is a spherical wavefront from every particle, ether particle here will be disturbed because the light that is coming here, and will emit what is called the secondary wavelets. You got a secondary wavelet, okay. Then it emits a secondary wavelet. The envelope all the secondary wavelets in time t, because v is the velocity of the disturbance, vt will be the distance that will be traveled by the secondary wavelet in a time t. So, you draw a sphere or a circle with this as the center, and you have got vt here, the circle is drawn here, and similarly circles are drawn here, okay, drawn here, and you draw them the surface passing through all the points here. This gives what you call the advancing wavefront. This is the original wavefront, this is the advancing wavefront. That is how light wave advances, right. The propagation or the movement of the wavefronts are explained on the basis of Fresnel's theory, a point source of light is from which you got a primary wavefront, secondary wavefront, then another wavefront, and so on. That is how the light is getting propagated. Let PQR be the initial position of the spherical wavefront. Eisen's principle, each and every point on the wavefront PQR acts as a secondary source of light and emits secondary waves. The secondary source, this is a primary source. Every point here P, Q, R, they act as secondary sources. They emit radiation or light from here. The envelope of all the secondary disturbances will give you the advancing wavefront and emits secondary waves in all possible directions with the same velocity of the medium. If v the velocity of the light in air medium, then vt is the distance through which the disturbance would have travelled. Hence, you ask the question, hence to determine the position of the new wavefront after time t, draw spheres assuming each and every point of the wavefront PQR as its center and Vt as the radius. This I told you Vt is the radius, right. The Vt is the radius, draw spheres or circles, then find the envelope of all the circles drawn, that gives them advancing wavefront. Okay. Then the tangential surface P prime, Q prime, R prime, which touches all the spheres in position, is a new wavefront after time t. From the figure it appears that there is a back wavefront, but of course, it is not a thing which is of importance. Then you have a point source, then this is called a plane wavefront, this one is called a spherical wavefront. Source is coming from a far off distance, a very large distance from the screen. Then you talk of the plane wavefront, Huygens construction of a plane, this is a plane wavefront, right, plane wavefront, the advancing plane wavefront and so on, right. The wavefront originating from a point source of light at a very large distance is called a plane wavefront. The shadows formed by small obstacles are not sharp, that is one point. This bending of light around the edges of an obstacle or the appearance of light within the geometrical shadow is known as diffraction. According to Fresnel, a wavefront can be divided into a large number of strips or zones called Fresnel's zones of small area, and the resultant effect at any point will be depending upon the combined effect of all the secondary waves emanating from various zones. The rectilinear propagation of light. You know, according to Newton, light travels in the form of straight lines. You have an object here, you have the shadow is formed here, right? You can see the shadow, right? The shadow is formed. How do you explain the shadow? Light is traveling in straight lines and you get the shadow, right? The formation of shadow can be easily explained on the basis of Newton's theory, but the same, but having talked about diffraction, what do you mean by diffraction? Bending of light beam. So, if you got obstacle, you may ask the question, you know, you are telling about bending of light beam. So, when a light is incident here, obstacle, will it not bend and fall in the shadow? How will you apply the formation of shadows? If you assume, if you say that light is capable of bending, the light is bending, right? Then when you have an obstacle, how will you, the formation of shadows, how will you apply the formation of shadows? Shadows are seen, you have got a object here, you have got this is my object, my left hand is the screen, and you see the shadow. The formation of shadows can be easily explained using the Newton's theory, but if you assume the wave theory of light, wherein you say that the waves bend, the bending of light is diffraction, then having accepted diffraction is there, how will you explain the formation of shadows? That is a problem that is one has to encounter. One is encountering, and so people try to explain. Let us see what explanation is given by Fresnel and Huygens to the important problem of formation of shadows. If an opaque obstacle is placed in the path of a light beam, a sharp shadow is cast on the screen, indicating thereby light travels in straight lines. This can be easily explained on the basis of Newton's corpuscular theory. I think that should be understandable. It has been observed that when a beam of light passes through a hole or narrow slit, then light bends, right? The bending of light is there. Shadow formed on the screen, as I told you, you got a light source, you put a sphere or a ball. I put a ball or something, right? I put something here, a ball or some sort of obstacle in a path of the light beam, then you get a shadow, right? The shadow is cast on the screen, the light source is here, you got a ball here or sphere, then the shadow cone, you observe the shadow, right? I can put my finger against near the wall, I get the shadow, and how to explain the shadow formed? You got the no intensity, right? There is no intensity. The bending of light is there, means if you talk about bending, if you talk of diffraction, a student can ask, sir, you told about diffraction, so the light beam will undergo bending, and then why can't you see light here? How do you explain darkness that is obtained here? The whole of the lecture I am going to discuss with you today is how to explain the darkness that is obtained here. That can be easily explained using Newton's theory, but having said light can bend, you can ask the question, light can bend, and what will happen to the light should fall in the shadow? How do you get the darkness? That is a problem. So, it spreads to some extent into the region in the geometrical shadow. Light actually bends shadow because the bending of the beam of light around the edges of an opaque obstacle, but the intensity of light inside is extremely small. I have to prove, Fresnel and Huygens really proved that light waves bend around obstacles. Even though you see a shadow, there is a light being found there, but the intensity is extremely small. That is the reason why it looks as if there is a shadow is obtained, darkness is obtained, but within darkness there is some light, but the intensity is extremely small. That is how one explains the formation of shadows on the basis of wave theory, because according to wave theory light should bend. Now, the problem is to explain the rectilinear propagation of light employing wave theory. Okay. ABCD is a plane wave front. What is a plane wave front? You consider a spherical wave front, a part of it a plane wave, or at a very large distance the source is separated from the screen, the distance is very large, then you talk of plane wave front. So, ABCD is something like the plane wave front, right? The plane wave front which I show just now, the ABCD is the plane wave front. A wave front is a region up to which the light wave has passed. So, the light wave is found here, right? In the ABCD is a plane where up to this the light wave has come, it is incident here, ABCD is the plane wave front. To find the resultant intensity at P at this point P, the light ray is coming here, right. Now, it has reached up to this region A, B, C, D, and these are called the frontal zones. This is the first zone, second zone, third zone, and why are they called zones, and what are half period zones? These things which I will be discussing now with you. To find the resultant intensity at P due to the wavefront A, B, C, D, I want to find the intensity at P due to the light coming from the wavefront A, B, C, D. A, B, C, D is a region or a plane in which up to which light has come, and I want to find the intensity at P, right. I am going to divide that the wavefront or the plane into regions what are called half period elements or zones. The Fresnel's method consists of dividing the wavefront into a number of half period elements or zones called Fresnel zones, and to find the effect of all the zones at the point P. So, this is the point P, the light is coming here, the light has arrived at the region up to the region A, B, C, D. A, B, C, D is a plane wavefront. It is divided into number of zones, right. O, P is a distance separating O and P is OP. So, B is the distance here. Now, from P you have this what is this? This is the greater distance, right, B plus lambda by 2. What is lambda? Is the wavelength of monochromatic source. P plus 2 lambda by 2, that is your the distance separating the M2 and P is P plus 2 lambda by 2, and M3 and P is P plus 3 lambda by 2. Okay. Then you, with P as the center, you draw the perpendicular, and this is the first half period zone separated by a distance B from P. So, PO is B, and on the other hand you draw circle with P as the radius and P plus lambda by 2 as the the distance. You draw a circle, that is the second half period zone. Then B plus lambda or 2 into lambda by 2 or lambda, this region, then this region, and okay, from P you draw circles, okay, with values like P, B plus lambda by 2, B plus 2 lambda by 2, P plus 3 lambda by 2, P plus 4 lambda by 2, and so on. And now, the resulting things are called half period zones. Why are they called half period zones? Because what is the difference between these two? Lambda by 2 and 2 lambda by 2 is lambda, 3 lambda by 2, the difference is lambda by 2, lambda by 2, lambda, 3 lambda by 2. What is lambda? Lambda corresponds to a path difference. We have seen earlier a phase difference of 2 pi corresponds to a path difference of lambda. 2 pi means what? It corresponds to a time period t. So, lambda corresponds to a period t, lambda by 2 will correspond to a phase difference of pi or a time difference of t by 2, because you got lambda, kind of lambda by 2, lambda, 3 lambda by 2, that corresponds to half the period. Lambda corresponds to 2 pi, 2 pi corresponds to a full period t. So, lambda by 2 will correspond to t by 2. The time difference between the light to come from here to here, lambda, then t by 2, t plus 2 t by 2, and so on. So, that is the reason why they are called half period zones, the first half period zone, second half period zone, third half period zones, and so on, right. So, this is the first half period zone, this is second half period zone from here to from here, the third half period zone, this region and this region, that is the second half period zone. If spheres are constructed with P as center, that is what I told you earlier, and radii equal to P plus lambda by 2, then P plus 2 lambda by 2 or lambda, and then P plus 3 lambda by 2, etc. on the wavefront. These circular zones are called half period zones. Each zone differs from its neighbor by a phase difference of pi or a path difference of lambda by 2. So, thus the secondary waves starting from the point O and M1 reaching P will have a phase difference of pi or a path difference of lambda by 2. Where are your O and M1? You have O here, M1 is here. These two, the light coming from M1 and O will lead to a phase difference of a path difference of lambda by 2 or a phase difference of pi. That is what I want to tell you. a path difference of lambda by 2, because the lambda by 2, then 2 into lambda by 2, that means lambda, then 3 lambda by 2. Between every half period zone, the path difference will be lambda by 2, or a phase difference of pi, or a time difference t by 2. T by 2 is coming, that is the reason why it is called half period zone. Okay. So, a Fresnel half period zone with respect to an actual point P is a thin annular zone of the primary wave front, in which the secondary waves from any two corresponding points as neighboring zones differ in a path by lambda by 2 or t by 2. O is the pole of the wave front x y with reference to external point, OP is the perpendicular to x y, and so on. In 1, 2, 3 etc. or the half period zones constructed on the primary wave front x y, OM1 is the radius of the first zone, OM2 is the radius of the second zone, and so on. P is the point at which the resultant intensity has to be calculated. OP is equal to B, OM1 is equal to R1, OM2 is R2, OM3 is R3, etc. right. Now, OP is equal to B. What is the light has come here, now we want to find the resultant intensity of the light that you have got here at the point P. That is what we have to find, that the plane wave front is divided into number of half period zones. Now, this OP is equal to B, and then OM1, OM2 values are given here, and OM1 is R1, OM2 is R2, OM3 is R3. You have got the first half period zone, the second half period zone, third half period zone, fourth half period zone, and so on, right. Let me now summarize from what I have told in this lecture. The points are the coloration exhibited by the compact disc, the CD, and the bursts are due to the phenomenon of diffraction. According to Huygens, light is a source of disturbance producing primary wave front and secondary wave fronts. Rectilinear propagation of light is being explained by constructing half period zones in the plane wave front. The questions are: mention some of the effects due to diffraction, explain Huygens principle, how does light propagate, what are half period zones. With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.